first slide because there's already been some introductions made. So these are 6 of the topics that I'm going to take you through. With this occasion, I should also mention my colleague Linda, who is on the call today, and he will take other topics that are included on the syllabus, particularly unsupervised methods. So I'm going to take you through these sections that you see on the screen. And today we are going to look through the first 3. And we have a second session on Monday and a second session, the last one with me, on Tuesday. And then Linda will take you through unsupervised learning on Thursday and Friday. So let's dive in. This module is called AI and Machine Learning for Mental Health. Now, although the name says AI, the focus is very much on machine learning. However, I thought it would be useful for us to look at some of the AI topics that could be applicable. So first, what is AI? AI is an area of research. A lot of people refer to it as being cross disciplines. So it touches on topics from computer science and engineering, but also from other fields, such as education, philosophy, neuroscience, biology, sociology. And the main purpose, or let's say aim of AI, is to build intelligent computational agents. Now, I've put computational agents in quotes because these agents are meant to be machine programs that run on a computer. There is a big discussion about what does it mean for something to be intelligent. And I'm not going to go into the history of that, but what I would say here is that we say that the machine is intelligent because it can perform tasks that require human intelligence, and they are complex. So I don't refer here to a task that is, let's say, automation. For example, calculations. Performing calculations with large numbers, it's something that machines can do faster and probably more accurate than a human can. But we don't refer to that task as being, the kind of intelligence that we mean in artificial intelligence. So we talk about intelligence as being something that refers to complex tasks such as medical diagnosing, playing more than just doing automatic tasks. And we equate this idea of intelligence to being rational. So if I was to ask you, would you describe yourself as an intelligent person? Of course, you'll say yes, and then I will ask you why. And that would be a bit more difficult for you to explain. So the same with intelligent machines, we have to come up with a definition that is something that is computable. So very much a definition that is related to a function, some kind of mathematical function that we can compute. So we talked about this idea of a machine being, or an algorithm being rational. So by that, we mean that it does the expected thing. And by that, we mean that it does some kind of actions that maximize a function. So it's as expected with respect to this mathematical function that we are trying to minimize or maximize depending on the task that we want to do. There are 2 types of AI. There is the weak AI. This is also referred to as the narrow AI. These are intelligent machines that are designed to perform well for specific tasks. For example, a machine that is good at natural language processing, a machine that's good at computer vision. So we also have another type of AI that people talk about, especially with the emergence of ChatGPT, and that is the strong AI. So the strong AI is the type of AI systems that incorporate human behaviors more prominently. So this would be referring to the ability to do multiple intelligent tasks at the same time. For example, not just being able to understand natural language, but also interpreting tone, emotion, and so on. And there are two substreams. One is what's called the general intelligence. So this would be machines that are as good or as intelligent as humans. And then some people also talk about super intelligence. So this would be machines that surpass human intelligence and ability. We are still in the realm of weak AI or narrow AI at the moment, but we can talk about this maybe later on. There are different types of technologies that incorporate AI, or technologies that are dealing with aspects of AI. So I've added a few in this slide. Natural language processing. So this refers to the ability of computers to understand language, whether that is written or spoken. Knowledge representation. This is about representing information about the world in a form that computers can perform tasks on. And this is not as easy as it might seem. We can talk about this a bit later. Speech recognition. So this refers to translating speech or text into a format that machines can read. And then there are some examples of applications or systems, if you want to call them, that utilizes this type of technologies. So we have Facebook, chatbots, and especially for mental health, there's a lot of interest in developing chatbots for mental health. And of course, this would involve using technologies such as this. I'm going to skip this one for the moment. Other types of technologies are computer vision. So this would be machines that are able to perceive their surroundings. We have examples such as Google Cloud Vision. So these type of machines are able to sense things in the picture, count objects, detect dangerous objects, and so on. So this is really centering around the ability of AI to sense things. Audio processing, this refers to detecting and translating audio signals, again, in a format that the machines can utilize. Another example, apart from Google Cloud Vision, would be Amazon Echo. So again, this would be utilizing computer vision and audio processing. Some examples of AI technologies that you are aware of. Now you're going to ask me, what's the connection between these and mental health? Well, it depends what kind of application you have in mind. I mean, you can think of facial recognition as being something that would be useful into an application like that. I'm not sure. Image categorization. So this would be an example of AI task and can be performed with machine learning. So this refers to the ability of putting images into different categories. So for example, facial expressions. Is the person smiling? Is the person frowning? And so on. Sound pattern recognition. So this is a classification problem. It's about classifying sounds into different categories. So you could maybe think of an application that is trying to understand the tone. Is the person sad? You know, is the person angry? And so on. Speech to text. This could be an interesting technology that could be utilized for something like applications to mental health, computer vision, and so on. Let me move on. This slide comes from a recent paper. And this paper was looking into how AI can be utilized in managing the patient flow. And you can see some of the things that I've been talking about here. So you have prediction, so tasks involving prediction. For example, looking at which factors affect the outcome of a patient. Will this patient deteriorate over time? And diagnosis, finding the right diagnosis for the specific condition that that patient is suffering. And you can see here that the kind of data that you would use for diagnosis would cover a multiple types of data. So it could be data collected from a survey, just like you've seen some of the examples already in this course, but it can be other things, image recognition, biomarkers, and so on. The applications in public health, so digital epidemiology, there are national screening programs, and so on, but also cost-effective solutions, how AI could be utilized to cut costs, for example. Therapy selection and generation, finding new treatments, remote therapy, and so on. Applications in administration and operations. So this would be automation of specific jobs, digitizing the amount of data that's being collected, let's say in a clinic, and so on. And then personalization. So as you can see here, there's a wide range of applications that AI, and through this I include machine learning, can be utilized. I tried to put together a little slide, but this is not complete. I wanted to maybe think about this with me. So we have types of applications to mental health. This is still a topic that is very much in early days. So therefore, there's a lot of scope to think about how AI can be safely utilized for something like this. So on the first column, you have early detection. And some of the examples that I think you've seen already in this course are about detecting, for example, mental disorder, okay? And a lot of these data sets utilize either self-reporting questionnaires or data collected from social media, for example. And this can cover not just messages that people leave, let's say on different platforms, so text that they write, but it can also be digital interactions. And by digital interactions, you can mean things they search for example, and so on. So you would say that, you want to utilize machine learning for early detection. You have to address the question of what data is suitable for something like that. And you need to be able to understand the quality and how relevant that data is to the purpose that you're trying to apply the data on. So then you have to think of the algorithms that are suitable for something like that. You want maybe to detect not just a current state, but maybe you want to look at changes in conditions like depression or anxiety and so on. And then coming back to the slides I've showed you briefly, you'll be thinking what kind of technologies are available for me to utilize. So as a let's say, computer scientist, you will still be able somehow to one, be very close to the data that you are trying to analyze, and hopefully this course can give us an idea of how to understand some of the algorithms, the machine learning algorithms that are available to use, and then how different technologies can help you with that task. And not only how they can help you, but what are the limitations. On the second column, I put diagnosis support with natural language processing. So you might want to say, I want to support the diagnosis of a specific condition. But, with mental health, this can be clinical, or this can be mental health that's been observed in the community. So these are two different things. I'm not an expert in that, but you will know probably more than me. So the purpose of such tool would be not to predict by themselves, but to assist medical professionals in making a diagnosis. So here you'll be thinking, what data do I have for something like this? What data is relevant? So I've put a little question mark there. And then you'll be saying what technologies are available. So again, natural language processing comes in as something that can allow you to detect linguistic components in the text or voice or the data that you are trying to analyze. Okay, in the middle, I've added virtual reality therapy. So this would be techniques or systems that allows individuals to deal with trauma or anxiety. So you would have maybe simulated scenarios or environments that these patients can be, exposed to, and to help them to confront their problems. Again, something like this would involve, understanding what kind of data can be used for something like this, and the dangers of maybe utilizing scenarios that, might not be contextually appropriate, or maybe you might introduce other complexities in that, and so on. Again, data is quite relevant to something like this, not just the technology. Personalized treatment. This is a very, big area, but again, very much in the initial stages. Can you use, for example, genetics, medical history, lifestyle, treatment responses, or other types of data so that you can develop personalized treatments for specific individuals? And, in this area, we talk about IoT. So this would be, sorry, I'm breaking. Can you hear me now?
Yes. Yes, you're clear.
Okay, so IoT, the Internet of Things. So this refers to interconnected devices that collect data constantly about a specific individual. And the idea is that you'll be using this to develop predictive analytics. And the last one refers to, improving patient flow. Again, data, and I left it open there because you might be thinking, what data do I have available? What's relevant, and so on. So these are, hard areas to venture in. Okay, so let me go next. All right. This slide, I'm going to spend a bit of time on it, not too much. How do we measure intelligence? So how do we measure that our tool is intelligent? So I thought I should include this one in here. It's a bit different than what you're going to see in the next slides, but it's something to think about. How do we measure that a system that we build is actually intelligent? And for historical reasons, but not only, I've added here what we call the Turing test. So for those who don't know what it is, I think it would be interesting for you to read about this. So this test was developed long time ago in the 1950s. And the idea of the test was that a machine is intelligent if it can fool, a human. In terms of the responses that the machine gives to an interrogator, to a human interrogator. So it consists of two rooms. One has a machine or an AI system. The other one has a human. The human asks questions to the machine, and the machine should respond to any questions. If after some time, the human cannot tell whether he's talking to a machine or to a human, then we say that the machine has passed the test. And this brings me again to what I've put on the first slides, is for us to build something that's truly AI, we need to cover these areas. So one is language, natural language processing. The other one is knowledge representation. How do we represent the complexity of the world, in this case, mental health, into something that's computable? And, that's usually numbers. How do we reason? So how do we teach machines to reason? So this is called automated reasoning, and then machine learning. So machine learning is one component of intelligence in terms of the machine. So machine learning should give the machines the ability to adapt to new circumstances and to detect patterns in the data. Okay. Considerations, and this applies to machine learning as well. It's general to AI. I've added 3 considerations here. One is trust. How do we demonstrate that AI is safe to use? We come up with a clever assistant, mental health assistant. How do we demonstrate the safety of that tool? How do we avoid biases? And then, how do we avoid risks? What measures can we put in place? The second one is liability. What happens when AI makes errors of judgment? What happens if it breaks the law? Who is legally responsible? And the third one is control. So especially when we think of supra-intelligence, right? What happens when a machine takes over a process? How do humans take the control back? 2 frameworks are available. So for those who are interested in this, they can look more into this. They are not the topic of this course. One is responsible AI. It's a framework that organizations can use to mitigate risks and challenges, defined by 5 principles: fairness, reliability and safety, privacy and security, transparency and accountability. Tools that can allow to verify results that AI is producing. Okay, and before we delve in machine learning, another maybe important distinction to make: there are 2 approaches to AI. We have the classical AI and the machine learning type of AI. So machine learning is the topic of this course, but I thought we shouldn't also forget that there is another approach to AI. This was very much used at the beginning of AI, and it's based on logic. So these are systems that are trying to capture the reasoning that humans apply to everyday problems. So machine learning is another branch, and this is the topic of today's course. Okay, questions. Let me break after introduction. I can leave space for some questions before we move into the machine learning topic, if that's okay. Melissa is asking a question on the chat. Right, so we have the logic-based. So very much you should think about expert systems here. Logic AI, and then machine learning, which should be tools that pretty much utilize vast amount of data module today. Sorry. All right, so I think actually we are starting with supervised learning now. Are there questions up to now? You are feel free to ask. You can unmute, perhaps. I'm not sure what's the procedure in terms of taking questions. Yeah, Melissa. Are you able to ask? Okay, maybe if you could unmute. I'm not sure how to. Let's see. So Melissa, Melissa, you said you have a question, and then you can say, oh yeah, please type. And then Princey, if you can verbally say your question, feel free. And Maurice. So Princey and then Maurice. Go ahead. If Princey isn't ready, Maurice, would you like to go first?
Yes, I don't mind. Thank you very much, Amelia, for the insight so far. My questions are two. One is, where does generative AI fall? Does it fall under classical AI or machine learning AI? Then secondly is that, are we going to cover, maybe I'm maybe jumping the gun, but are we going to cover in this course, because I joined midstream, are we going to cover some of the ethical issues around AI, especially around using AI for research or for subjects like healthcare and so on? Thank you.
Thank you for the question. Let me take another one before answering. I'm not sure who is. Okay, Florence is asking about model deployment. Let's hope so. I was planning to. Let me just also take some notes. Okay, so I'm not sure if somebody else has a hand up, but yes, so Florence, your question, I hope we can do that. I mean, there are many ways to deploy a model. So I don't know if you mean deployment on the cloud, but we could maybe see if we can cover something like that, and I can prepare a demo. Okay, so let me answer the question about generative AI. Where does generative AI fall under? So I think, and maybe if there are experts on the group, they can come in. It falls under natural language processing. So we have, of course, generative AI in terms of generating text, but we also have generative AI generating images. So you could, let's say, cover natural language processing in terms of text and audio, but it can, but then you can also think of video and image. It's not yet supra intelligence. I mean, this is a debate, right? Because people were expecting to see the latest model of GPT. Will it be able to achieve that, supra intelligence? And if you read the news, there was a lot of, debate about this when OpenAI went through some internal turmoils. So, so far what we see really is not supra intelligence, right? It's still narrow AI and is still in the realm of NLP, video and image processing. Okay. Princey, would you like to go next? Or you can type. Would that be a better option? So Prince, if you can type your question, that would be great. And then we can come back again in the next session. So let's go into supervised machine learning, right? So as we said, there are two types of AI that we know of: the logic-based and the machine learning type. A little bit of history. So this is not extremely new. The first mainstream machine learning program was used to develop a spam filter, and we are going to take an example like that today. And in 2006, we saw the first breakthrough, let's say, in machine learning with a paper published by Geoffrey Hinton. And he was utilizing deep neural networks capable of recognizing handwritten digits with a high precision. And this technique is called deep learning. So a deep neural network is a simplified model of, the model of the brain, which consists of neurons interacting with each other, connected with each other, and transmitting information. Why was this an influential paper? Because at that time, training and use of deep neural networks was considered quite impossible. But nowadays, we are utilizing some of these algorithms even in the gadgets that we own. Applications of machine learning: classifying news articles. So for machine learning, you can think of classifying a text with respect to the nature of that text. Does it describe, suicidal thoughts, for example? So this is an example of natural language processing. Another example is automatically flagging offensive comments on a discussion forum. This is an example of text classification. Analyzing images, in this example is products on a production line to classify them. So this is an example of image classification. Detecting tumors in a brain scan. This is what we call semantic image segmentation. Forecasting revenue based on performance metrics or history of past revenue. This is an example of regression task. Detecting fraudulent transactions. This is an example of anomaly detection. Segmenting customers. I mean, for mental health, you might be thinking segmenting students based on, whether they suffer from anxiety or not. So this is an example of clustering, recommending something or products for a client based on similar things that person bought. That's a type of recommender system. Building an intelligent bot for a game, for example, this is called reinforcement learning. So quite a few types of applications. And as you can see, it covers natural language processing, classification, regression, clustering, in terms of segmentation, anomaly detections, and so on. Two definitions. And the reason I put these definitions here is because one is pretty much informal. So the first one by Arthur Samuel describes or defines machine learning as the field of study without being explicitly programmed. But what does it actually mean? So such a definition has to be made a bit more formal because we are dealing with machines. So something that's formal but not very formal. So when I say very formal, I mean mathematical, right? Described as some kind of mathematical function. So the other definition says a computer program is said to learn from experience E. So you have this experience E And so this experience E is a representation, right? Is a representation of some real world scenario in numbers, for example, right? So an experience E with respect to some task T and some performance measure P. So we have an experience, a task that we are trying to do, and that can be classification, anomaly detection, and so on. And then we have a performance measure P. And this performance measure P is a mathematical function of some kind. So we are saying that a computer program learns from E with respect to T and some performance as measured by P improves with experience. Okay. So let's have a look at a concrete example of how we could break this definition down. So let's think of the spam filter as being an example of early application of machine learning. So what's the task? Well, the task is to flag new emails as spam or not spam. That's what we want our model to be able to do. What's E? So E is our experience. We also call this training data. So in this example is a pair of emails with a label, and the label indicates whether that email is a spam or not. And now we have to think of a performance, how we are measuring that performance. So in this case, we have to have some kind of function that measures how correctly the classification is being applied. So how correctly does the algorithm catches a spam message and labels it as spam, for example. This looks a bit complicated, but it's good to discuss this in the early stage. So let's go back to this. So we have the task T, we have experience, and for supervised learning, this experience is a training set. It's a collection of data points and their label. So we have seen them before, and we applied a judgment to them. So what is this performance P? How we talk about 4 situations. One is true negatives. So these are this case classification system correctly predicts a positive case. So if an email is spam, our system is able to say, yes, this is a spam. So that's a true positive. Now, let's think of another example. For example, an antivirus classification system. So this would be a true positive would be a program that is infected with a virus and is caught by that antivirus program, right? So it's classified as infected. So it's a true positive. But let's think for mental health, right? For mental health, if you have some kind of system that is trying to, classify whether somebody, suffers from depression, so, according to some measures that you have in place, then you would say that a true positive will be an individual that suffers from this depression, so in reality, and is correctly identified as such. Okay, then we have true negatives. So true negatives would be cases in which the individual does not suffer from depression and the algorithm identifies him as not depressed. Okay, so it's a true negative. And in terms of our spam example, emails that are classified as not spam and are truly not spam, right? So these are the safe emails. They are safe and we classify them as safe. False positives. So these are where the tricky bit comes in. So we have the false positives and the false usually refers to rejection of a null hypothesis when the hypothesis is true. It might sound complicated, but basically in the spam example, a legitimate email goes into your junk folder, right? So it's a false positive. It's not actually a spam, but it's classified as spam. Now, you might say, I'm going to live with that. Okay, I'm going to check my spam folder all the time, right? What's a false negative? This is even more difficult, I think, to think about. So false negative would be a situation in which the algorithm guesses a negative class for an output, but the output is actually belonging to a positive class. So in the example of the spam email, you have a spam email that's classified as legitimate. So the algorithm says it's not spam, right? It's legitimate, okay? But actually it is spam. All right, so with this introduction, when we measure the performance of our model, we are measuring this, especially for classification problems. So we are interested to know the true positives. So you can kind of imagine that all your data sets will be classified as one of these. So true positives, and you probably want to maximize that. True negatives, right? And then you have these gray areas where you have false positives and false negatives. Now, depending on the problem domain, you might want to emphasize, or let's say eliminate, you might want to eliminate the risk of one versus the other. Because as we said before, if a data set has to belong in this. Right. So positive can become after being reviewed. So it leaves and I mean, don't have severe implications to some. So attention. Let me switch to this internet. Hopefully, this is going to work. Just give me 1 minute. Can you hear me now?
Yes.
Yes, we do.
Hello?
Yes.
Yes, yes, yes.
Yes,
Yes.
yes.
Okay, great. So let me continue. Just give me 1 second. I will share my screen on this other machine. Okay. Give me 1 minute. Oh, stop video. Right. What am I doing? Right. Okay. Can you see my screen?
Yes.
Yes.
Okay. So we have this matrix, and you can see here that what I have in this matrix is basically the measures that we've just discussed. So you have the classes appearing across the row and columns. So in this case, you're trying to
Yeah.
Um,
Amelia, we can hear you.
Let's just wait a second. Uh, Kindly let's give Amelia some few seconds as she check her internet.
Okay, apologies. I'm back. We have some issue. I think it's a countrywide issue. I don't know if you can hear me now.
Yes, we can hear you now.
Yes,
Yes,
because
we
I've
can hear.
tried three different internets have not worked. So bear with me. I think we are having an issue. All right, so let's go back to here. So we have what we call a confusion matrix, and this is showing us the accuracy. And the accuracy is basically true positives and true negatives. So these are the ones that the model gets right as a proportion of the total. So you'll be saying, how accurate has it been in terms of detecting the true positives and the true negatives? And then we have what we call sensitivity or recall. And this is the true positives as the proportion of the true positives and the false negatives. Why is that? It's because, of course, we want to distinguish, the model should be able to distinguish between the true positives and the false negatives. So it should be able to do that well. And then we have what we call specificity. So I left a blank there for you to think about. So specificity is looking now at the true negatives. So this is what the model gets right in terms of classifying as, negative, depending on what the class is. So in this case, the true negative would be, is not depressed. Okay, the person is not depressed and is predicted to be not depressed. So you can maybe tell me later what should be this proportion out of. And then we have precision. So precision looks at the true positives as the proportion of the true positive plus the false positive. So is it precise? Is it able to distinguish them really well? Now, the question is, what are the risks of these errors? So if we have these errors, and every model has these errors, what risks are we running? If one of these, let's say sensitivity is low, for example, what are the implications? Now, there are other calculations or measures that you could use, apart from the ones that I listed at the top. So we have the Cohen-Kappa index, and this is something that probably you'll use a lot in the type of mental health that you are doing. Then we have the F1, which is a harmonic mean, and then we have the Yunden index below. So any model that we might run, any machine learning that we might run, supervised machine learning for classification, will have these types of measures for performance and accuracy. Okay, so let's look at the Kappa index, because I was saying it's something that you'll probably use a lot. And this is measuring the rate of agreement. Now, for a classification problem, we can think of the rate of agreement between the predicted value and the real value. But in other types of studies, you can think of two individual raters. So two individual experts who look at the same case, and they rate that case as depressed versus non-depressed. And then you want to see whether, how much these two agree with each other. And this is a measure of, you're calculating two probabilities. So the first one is looking at the rate of agreement. So if you look at this example, the two raters agree in 36 cases out of 50. So they both agree in 17 cases, right? So we can see the ones that are happy, and they're classified as happy. So they both agree in there. So those are the true positives, right? And they also agree in 19 of the depressed cases. So those are the true negatives, right? So we have a rate of agreement of 72%. So that's the P0 that you see in that formula to the left. And then we have this PE. So this PE is the hypothetical probability of a random match. So what you want to know is that the assessment of these two raters or doctors is informed, cannot be by chance, purely by chance. So you want to know whether they've come to the same conclusion through, judgment or information, and not by chance. So this is this PE value that you see there. And it's calculated as below, right? And what are we doing there? I mean, maybe this is a bit more detailed than you need, but let's look a little bit at this. So what you see here is that we count how many are across the columns and the rows. So you can see across the first row, there are 25 observations. 25 observations, out of which 17 are not depressed and 8 are depressed. Across the second row, there are again 25 observations, and the same across the columns, 23, 27. So you can see here that I do something like a weighted sum, so to speak. So I'm saying that for the ones that are, happy, right? Yeah, happy for the rater 1, happy for the rater 2, 25 out of 50 for the rater 2, so you can see them there. And then for the other rater, there are 23 out of 50. So we calculate the product of the two. And then we do the same for the sad ones, or the depressed ones, right? So there are 25 depressed observations for rater 1, and there are 27 depressed observations for rater 2. And we do the multiplication. And out of that, we come to the left, you have the interpretation. If the agreement is moderate, substantial, almost perfect, and so on. So this is another measure that we could utilize. So I wanted to give you a class exercise, but let's see, due to my issues with the internet, maybe we are running late. But yeah, let's try to spend 5 minutes on this. And what I would like you to do is to take these two examples and think what could be a true positive, what could be a false positive, what could be a true negative and false negative for an AI that screens for cancer, for example. And then the second one, this is an AI that diagnoses mental disorder. So let me give you 5 minutes, and then I have a chance to catch up with the chat. Is that okay? So if you could write down what constitutes these true positives for the two AI systems that you have there, and so on. And then we meet at, let's say, 11 minutes past 2, 5 minutes to discuss. Hopefully that's okay. I didn't get it. Okay, somebody didn't get the task. So what I would like you to do is to look at the definition that I gave for these true positives, false positives, and so on with respect to a classification problem. So those are on the slide above. So there's a slide above here, slide number 22, that looks into these measures of accuracy. So when we look at whether a machine learning model performs well with respect to a classification problem, we look at these measures, true positives, and so on. And then what I want you to do is to apply this and try to understand what could be the meaning of these true positives and so on for the two examples given there. So a machine learning that screens for cancer, and a machine learning algorithm that is diagnosing mental disorders. Okay, so the first answer there, La Mesa, yeah, true. So in the first example, somebody being screened as positive, and truly it has cancer, right? So it's true positive, yeah. Yeah, so I think the messages are coming. There was another message there, but it disappeared. I wondered how. Yeah, so false positive would be somebody who does not have cancer, but is classified, right, through screening as having cancer. So that's a false positive, false negative. Sorry, false positive. Right. Okay, correct. I see the good message, good responses coming through. So while you are thinking about this, in the interest of time, let's think about how significant these are, right? So there's a study, and I put a link at the bottom of the slide that takes you to a calculator that was created as part of that study. Now, what that study tried to do, it tried to arrive at some kind of measure of how many of the likelihood that somebody has a false positive result in their lifetime, right? So they looked across, different data sets, and they derived this probability that a person or an individual will have a false positive. Now you can kind of see or imagine that these false positives, the number of false positives is correlated to the number of screenings, right? The more screenings you have, the higher the chance that you'll have a false positive, right? And I'm not going to go through this study. It's quite interesting, some of the points that the study makes. I've put them at the bottom of the slide. So females had a higher lifetime probability of a false positive, and probably because they screen more. And each health body, and I would like people who are in the audience who are in the know, and they are medical professionals, to come and tell us more about this. But each health body has some guidelines regarding to the type of test that somebody should have across their lifetime. So females have a higher chance of getting a false positive. Now you'll be thinking about the implications of that, right? Okay, so what I'm trying to say with this slide is that it's important to think about this in the context of the AI solution that you're going to develop. And it's also important to understand as much as you can the implications of having, let's say, more false positives versus others, and what are the risks of that happening. So this comes, this discussion, maybe in terms of mental health, is not something we can do in this course, and it would be interesting to know more from you because you are, experts in that field. But some of the facts that I gathered are these: that in order to diagnose mental health, there's a reliance on the conceptual validity of the diagnosis criteria. So you're coming up, you're relying basically on the fact that those questionnaires or those methods are reliable. Things get complicated when you diagnose people in the community, right? Community studies versus clinical settings. And usually, according to the literature, prevalence of mental health resulting from community studies is higher than what's reported in clinical settings. And, again, what's the implications of that? The other thing to note there at the end, that there is a need to think about these contextual qualifiers. So these are key to reducing the false positives. So if our questionnaire says that somebody is irritable, right, versus somebody whose irritability is abnormal and persistent, right? So these are two kind of different features, and you can't understand them from the number. They have to be interpreted using these contextual qualifiers. Okay, so let me go to the next slide. So I want us to look at what's different from the machine learning approach versus the traditional approach when it comes to algorithms. So this slide is giving you an illustration of the traditional approach of solving a problem with the machine, right? So, or a computer. So first we study the problem, and this is where we have our context, guidelines, and everything. Then we write some rules. Now, of course, those rules, they go through some process of knowledge representation, knowledge engineering. They are not going to be perfect. And then we have an evaluation of those rules. So we write those rules. For a computer program, you can think about them as if-then rules, for example. If the email contains this feature, if the email contains this other feature, then evaluate it in that way. So we have an evaluation, and we have this error analysis. And I've discussed some of the measures used for analyzing errors. And when we are happy with this cycle, so we study the problem, we write rules, we evaluate, we analyze, we can launch a solution. Okay, now what does, we can think of ethical issue coming being at play in all these stages, right? In all the stages that you see here on the slide, you can think of them. Studying the problem. Ethical issues could be related to how we classify some condition as being a condition, right? A disorder. So, that could be an ethical issue. Then it comes to training the model, in terms of the data. Is the data representative? Are there biases in the data? Is the data sufficient? And so on. The other thing comes from here, from inspecting the solution. How do you test? That's one of the issues that we are facing in machine learning. How do you test something? You can't test something, at infinity. That's where the traditional approach, you could say, okay, it was on a safer ground because you could write some test rules because you understand your rules, you see them. Whereas with the data, the assumption is that those rules are in the data and you're learning them. So there are complex problems to be considered. Okay, so I'm going to skip this slide for now. And I want us to look at, try to get closer to running something together, hands-on. And to do that, let's just look again at what this supervision does. So in the context of a spam, right, I have a training set. So this training set contains emails and labels. So the ticks represent safe emails. There's no spam. Those are not spam. And the danger sign for those emails, those are dangerous emails. Now, how do we know they're dangerous emails? Well, because the human labeled them. Yes. So sometimes your email provider asks you to tick and say, this is spam or this is not spam, right? So you are applying a label. So the idea is that this training set is fed to an algorithm, a machine learning algorithm. And that algorithm should be able to classify a new instance. So when it sees a new email, it should be able to say whether it's spam or not. Now, unsupervised algorithm, and this is something that my colleague will take you through, this assumes that you don't have labeled data. The data is not labeled, but your data comes with characteristics that are in the data, right? And you are able to group things. You're able to find groupings, clusters inside your data. So, you know, your training set is not labeled, but somehow you are able to pull together individuals with similar characteristics. All right. I will come back to this slide. Let me just move on. This slide is for you to maybe look at. There are a lot of data repositories that you can access, and some of them have open data sets, and some you can obtain by request, and so on. So I will invite you to look at some of these things. So let's discuss now about how we could build something like this. So this is what we want, right? We want some kind of algorithm that takes in a training set and then is able to classify things. How do we build it? Now, we have had what we call decision trees for some time. So these are algorithms that in effect, help you make a decision. So in this case, the decision is this email spam or not, based on characteristics of that email. So I think we should look at these decision trees before we run some code. So a decision tree is like a flow chart, helps you reach a decision based on a series of factors or questions. So in the example on the right, you have this decision tree that is taken from Wikipedia. This is the Titanic data set, trying to understand or calculate the likelihood of somebody surviving the sinking of the Titanic. So you will have all that data that's been collected regarding survivors. And you can see that some data has been collected regarding the gender of that person, the age, whether the person had siblings on board. And then we have the target variable, or the one that we are trying to classify, is whether somebody died or survived based on these features. Now, I mean, this is a simplified data set, right? But you can see how you would go about making sense of that data through such a tree. So you say, well, if somebody is male, yes. Is he older than 9.5 years? Now you can see there that you have, 61% of people in that category, right, died. Okay, and then 0.17 is the risk that the probability, right, that somebody has of dying based on this tree. Yeah, so you can see here that the females are on the right branch. Yeah, we have 73% of females survived
right? So the risk of, the probability of surviving is high, 73%, and females represent 36% of the whole data set that we have in there. So decision trees are used for classification and regression tasks. This is another tree, and I took this from the paper that you see at the bottom of the slide. And what they tried to do in this paper is to validate the use of a decision tree. Sorry, I'm not sure how to close this thing. Floating, 1 minute. Okay. So this would be a model that tries to validate a regression tree that is predicting how many people, what's the risk of somebody taking leave of absence or long-term sickness absence due to mental disorders. And you can see, again, this idea of decisions, right? So we have distress, the risk of being, you can see here there are 51 individuals who have taken long-term sickness absence due to mental disorder out of a total of 1,736, right? And this distress can be classified according to 3 levels: low, moderate, and high. So you can see these 51 individuals are split across the 3 classes that you see there. So 20 have taken long-term sickness absence due to mental disorders due to low, what's considered low kind of factors. Moderate distress, there are 21, and high distress, 20, and so on. And then further down on the tree, you see other features that help distinguish these 51 individuals. So you can see on the low branch, 10 are men, 10 are females, right? And there's not a lot of difference in terms of the risk. I mean, there is a difference, but it's not large. But then when you look at moderate, you see that when it comes to women, right, those who had a work pace that was high versus people who had a low work pace, the risk was much lower. So you see a substantial difference there. So this is how you would use a tree like this. And in this paper, they were trying to validate whether this tree helps calculate the risk. There are 3 types of decision trees in terms of how you would build them. And I've added some slides that describes how cart trees are being built. So we can come back to this because it's a bit mathematical. We can come back to this after we take a little example. So let's look at some, let me just do a new share. So I don't know if you were given a link to the resources, but if you haven't, I can ask maybe one of the APHRC team to put it in the chat. So I want us to take the first example. Okay, so the first example, it's about spam emails. Okay, give me 1 second. Classifying spam emails using R. So let me share my screen. And you can see my screen. No resources link. Okay, let me get the resources link. Just give me 1 second. I've just shared that in the chat. If it doesn't work, then just let me know. 1 minute. Everyone, let me share it to everyone. Okay. Right, so let me, right, so I've shared the resources link in the chat. Let me just use R. I was told that you did R. And what I'm going to do is open a project. So if you were given the resources, what you're going to see is there's a folder called ML for Mental Health. And inside the folder, there are 2 examples. So the one that we are going to look at now is the decision tree example. So what I'm going to do is open that folder. So I'm going to open the folder, the project. And when I open this project, you should be able to see the resources that belong to that project in the files window in R. So you'll be seeing the R file with the code and the data. So I already ran this before, so I already have some data in the data tab, and then the files come in the file tab. So let's look at this. I think that what I should do is give people time to install some of these libraries, because you might not have them. They're not too large, so I think you should be able to catch up with me as I'm talking. So what I suggest you do is run the cells one by one. I mean, just as an advice. And if you don't have the library, then you'll be using install. So you're using install packages and then just put the name of the package. So let's say if you don't have tidyverse, then you'll be typing tidyverse there. Let me clear this, yeah. And that should install the package. So what you could do, just run this one by one. So, you know, I have these packages already. The only problem is I'm working with 2 different versions of R, but it still works. And all I will do is just run them one by one. For you, you'll probably have to install them. Okay, what kind of data set are we looking at? So we are looking at a data set that contains 4,601 email items. Now, these are not actually emails. They're not emails. They represent emails. So if you look at the email data, yeah, so if I double click on it to see what's in the data set, then you're going to see that, you know, this data set represents emails. So remember our discussion there about knowledge representation, right? We can't put everything into the machines. We need to be able to represent that somehow. So in this case, each row or each record represents an email, and across the columns, you have some characteristics of these emails, including the label. So yes, no is what tells us whether something is spam or not. So yes means that it's spam, and no means it's not spam. And you could run a help on your data set, and this will then open in the help window some information about this data set. So you can see here that this data set consists of 4,601 email items, and 1,813 are spam. So coming back to our PowerPoint here, yeah, this is our training set. Yeah, and out of them, 1,800 and something are spam, danger. Okay. The other thing you see is the meaning of these columns. So you can see here that these have been pre-processed already. Yeah, data has been collected already on some characteristics of these emails. So the first characteristics is total length of uninterrupted sequence of capitals. So maybe the assumption is that if your email has, you know, long sequences of everything in capital, text in capital, maybe that's potentially something spam. If it includes a $sign, maybe it's to do with money. And you can see there's another characteristics down there that talks about the occurrence of the word money as a percentage of the total number of words in that email. So maybe if it refers to money, maybe somebody's trying to fish, or it's a phishing email, is trying to extort some money from you. So the $sign is a feature. The occurrence of the word money is a feature. There is also this bang, this is exclamation mark. So maybe lots of exclamation marks are trying to prompt you to do something, to act quickly. Maybe you want something, right? Click on this, and so on. Also numbers, occurrence of the 000 as a percentage of words, and the word make, right? But you can see that, you know, these features are characteristic to that data set. I mean, the data set is in English. I mean, probably in a different language, you'll be looking at other types of trigger words. And then finally, you have this yes, no. So this is the outcome label, labeling a message whether it's spam or not. So that's our data set. And what we are trying to do is to see if we can train a supervised machine learning algorithm that is helping us detect whether something is spam or not. So that's what we are doing. Now, one thing you could do is you could visualize your data. So I just put some simple visualization here, nothing complicated. So you can see the proportion. So it's not very balanced, right? We have, but it reflects reality, right? Because the class of spam email is usually smaller. And we refer to this as balance, class balance. If we want to see, oops, I have some, or did I not got my data probably? All right. Computing aesthetics. X class. All right. I think I added something there. So I'm going to replace that to yes, no. I think I had something before. I was doing something else before. All right. So here you can see that, you know, the two classes yes, no that we have in terms of occurrence of the word money. You can see for the ones that are spam, which is this one, the blue, there's more currencies, it's more dispersed, right? Whereas for the ones that are not spam, the occurrence of money tends to be low. It's kind of concentrated here and in this area, 0 to 2. We can look at all the features somehow. So here, for example, I'm looking at only the ones that are spam. So the ones that are spam containing capital letters, right? So we are looking at this the number of capital letters sequences that appear in the message. And you can see that most of them don't have, you know, large sequence of capital letters. Okay. I'm trying to think here whether I'm actually using the latest file that I gave you. Sorry for this. Probably. Okay, let me run this other one. So this one shows that actually these features, like for example, bang is exclamation mark. You can see that, you know, many spam emails. So see here, we are only looking at spam emails. You can see that none of these features is completely discriminatory, right? So you have to use a combination of these features to tell you whether something is spam. Because if you look at each feature individually, like for example here, exclamation mark, you know, 600 messages out of 1,800 of spam don't have any, you know, the frequency is 0, basically, don't have any exclamation marks and so on. So one feature is not enough to help you classify these messages. So let's try to use a machine learning algorithm from the libraries in R. So I'm using this library here, the RPart, sorry, the library RPart. So this is a recursive partitioning for classification, regression, and survival. So I'm using this library to build a classifier. So what we are doing first is we are setting a seed. So this is typical in machine learning, but also anything that uses random generation of numbers to help you replicate results. So if you can imagine, if I don't do this, then I could be in a position that I'm running this code today, I get some results, I'm running the same code tomorrow, but I'm actually generating a different model. So to help you run the same model every time you run this code, we are setting this seed, and it can be any number, 7, 1, anything. And what I want to do now is to split my data set. So I have all this email data, and I want to know how many or which ones to use for training. So I put them in the training set, and which ones I'm going to use for validation. And I put those in the training set. So to do that, you generate this index array. Now this index array, as you see, is randomly generated. And what I'm doing, so if you run this and you look at the array here, int, you'll see that for every single data point, I have 4,600. I put a 2 against, it's a bit like me going to the room and counting and asking you to shout a number, and the number tells you in which class you belong. So that's basically the idea. So it tells you for each record in which class it belongs. And you want this to be fairly random, right? So the chances of something belonging to one of these 2 data sets should be equal, right? So that's what we do. So we generate this array of indices telling me in which data set each email record belongs to. And then we start training. Sorry, we take out the ones that belong to the set number 1. So that's used for training. Yeah, so you have lots of them used for training. We take the ones that belong to set number 2. So that would be your test there. And we now train a classifier. So if you look at this, let me see if you're, oh, I'm talking to myself because the internet died. I tell you, I hate internet. Why can't people have face-to-face classes? Oops, maybe I am online.
Yes,
Sorry.
you are, Amelia.
You know, I'm getting a bit confused now. Okay, let me go back to the R. Sorry for this. 1 minute. Okay. Hopefully you can edit this video, right, before sharing out. Right. So if we look here now, we basically build a decision tree. That's what we are doing. We are building a decision tree using this RPart. Here we are saying what is our target variable. So this is the one we are trying to predict, yes, no, whether something is spam or not spam. And then here with this dot, what you're saying with this dot is you're using all the features, not just one. So if I wanted, for example, just to look at money, how many, only the feature that counts how many times the word money occurs, I will put that feature in there. And this will then only look at the predictive power of that feature, not all of them. If you want to look at all of them, and remember we said when we look at this histogram here that none of this feature is sufficient. You have to use all of them in combination. right? So that's where you have that dot. And then we are using the train. So we are building this tree using the training data. So let's run that classifier. So if it's successful, we would have built a tree, and you can plot the tree. So you can see with rpartplot, I am printing the tree. I have this extra here. So this extra adds extra information in the node. So if I put it to be 0, then I will not have the number of samples that belong in each class in the nodes. So that's what that extra does. And you can look at the library to tell you a little bit more about the other variable, like what does type mean? So here I'm showing how many samples belong to what class. So you can see that we said that there are how many messages that are spam. Let's look up there. 1,813, right? So 1,813 are spam, right? Now, what do we see in here is that we have a cumulative of 2,305 that contain dollar in that proportion, less than 0.056. And how many are in the no branch? How many are in the yes branch there? So this is our tree. Now, how do we use this tree? Well, we use this tree whenever we see a new spam message to take it through our model. So we look and say, starting from the root of the tree, we are asking questions about our email. And we say, well, does our email have this feature? Yes. And that's going to root us on the yes branch. And then we take each feature one by one, and hopefully will help us to classify whether the message is spam or not. Okay. Maybe I should stop here to ask if there are any questions, just to test how the room is. Since I shared my screen, I can't see the controls. Let's give me 1 second. Oops. So how do I see the controls? I am not sure. Zoom, let me have a look. No. Okay, are there questions?
You have to stop sharing first.
Oh yeah, but now I can't see where the controls are. That's my problem. Right. Oh yeah. Okay, I have managed. So let's see if there are questions and if people manage to download the data.
We have a question. Someone is asking, how can we add the percentages to the tree?
Yeah, I can see that. So what you need to do is check the type. So you are playing with the type. So here the type equal to 1, I'm showing exact numbers. So if you look at the library of the rplot, yeah, you'll be able to see what type you should be using in order to display the percentages. Yeah, so the data is in R. It should be in the folder that was shared with you. Let me just look at it. So the data should be in the folder and is called Oh yeah, sorry. The data, apologies, this is the spam. So the data belongs to this, apologies. The data belongs in this library, in this module called DAG. So you have to import this library in order to be able to get the data for the spam. So this is a data set that comes with that library. So you'll have to install that library and add it to your file. Anna.
Yes, thank you so much for this class. I would like to know, so from the decision tree, does it tell us what are the predictors now of the spam emails?
Okay, so this one is giving you the class. It just tells you this is a yes or a no.
Okay. And what do we have to do to identify the predictors?
Oh, you mean the features?
Yes, for instance, you said from this data set we have money and we have other predictors for spam emails, right?
Yes.
So how do you get to derive the predictors of a spam email? Do we still use the decision tree or there's another way to arrive to that?
Okay, so let me see if I get you. Are you asking how has somebody come up with these features?
No, but how do you get to know the predictors of getting a spam email?
Yes, so basically what you're asking, why should dollar, the presence of dollar sign, how many dollar signs are in an email, be a predictor, right?
Not really, but I want to understand if what you have just described is correct. So we have the predictors dollar, bank, money, and something, right?
Mm-hmm.
The spam email. So is using a decision tree going to tell us that, for instance, dollar and money are the predictors of spam email, or a decision tree just shows you these people belong to this category only? It doesn't go beyond telling you the predictors of now getting a spam email.
Okay, so that's good. You're asking this. So we skipped those slides, but I want us to go back to them. So how are these trees built, right? In what order you are, which feature do you look at first? So you can see that in this example, the feature that's in the root is to do with, how many times the dollar signs appears. Why is the tree built in this way? So, for one classification problem or decision problem, there are more than one tree that can be built. But the trees will differ in terms of how good they are at helping you classify. So we haven't looked yet at that aspect of, looking to try to see how good these models are, how good they are at predicting, right? So if I print, you see there's another command there, print CP tree, right? So print CP tree will print information about how this tree was built. So you can see here that the algorithm, through the mechanism of the algorithm, decided to use these variables in the tree construction. Now another thing you're going to see here is that this tree is limited in terms of the level, how big it is. So, so not only you can have more than one tree for one classification, but you can have trees of different height. So this is where we talk about, for example, overfitting. So if you can imagine, if you have a very, very large tree, then you are likely to overfit the data. to be very specific, to in terms of the features that characterize something as being spam and not spam. So there's also a cutoff point. So these algorithms use a cutoff point at which it's not worth adding more features and is not worth adding more levels. In other words, the discriminative power of the model doesn't improve very much. So this is what I wanted to look at. I mean, it's a bit, let's say maybe technical, and we can talk about this. I'm not sure what's the right order, but if you look at this slide, for example, I'm explaining some of those numbers. So that principe, that complexity parameter that is being shown there, discusses this idea that the size of the tree and the error, because what you're doing with these models. Sorry, there's a background. Maybe somebody can mute. There's a lot of background noise. I'm not sure where the noise comes. Okay, I muted. Yeah, so if you look at this, basically what you're trying to do with these models, you're trying to minimize those errors, right, that we talked about before. You're wanting your model to be accurate. You want your model to be specific, to have a high specificity. So how are you going to do this? Well, through those iterations that I discussed before, you iteratively reduce the error. Now, it's not easy to measure the error if there are many variables at play, right? So in this example that we see here, we are looking at what we call a threshold. So this is that complexity parameter. So this is a threshold under which splitting a node is not improving the complexity. So our tree only has 2 levels, level 0, level 1, level 3 levels, right?
Yeah.
And then you're looking at how many splits were made up to that point to find a decision, basically. And then you're looking at the error relative to the root node. So there's some of these measures that are used to help you build a tree. Now you can force the algorithm to give you a bigger tree. You can, maybe insist on some features versus others to be selected. But in this example, we let the algorithm decide, which feature to use. So here we didn't actually specify. Yeah.
Yeah, thank you so much.
Okay. So we can come back to this also in the next lesson. Now, don't worry, it's not 74 pages because I put other type of explanations in there. But so if you look in here, we'll do only one example today. It's only up to 54, slide 54. So not 74. So let's try to continue to look at something that's a bit more intuitive than the errors that we saw for that decision tree. And we are going to look at this confusion matrix. So in the code, what I'm doing now is I'm using the output here, and I'm deciding which threshold is optimal. So I'm reading these numbers, and maybe I should give you a bit of time to read this slide. And based on reading these numbers, I decide that the best threshold to use is 0.07444. So with that threshold, you construct, let's say, an optimal tree. So I'm going to run this again and plot the tree. And it will look the same because it's the same tree, basically. And then I want to now look at the true positive and the false positives situation. So I'm going to run a confusion matrix, and you'll see some of the numbers appearing in the output in the console. And you'll see what type of prediction has been happening here, right? So we have 1,278 messages that are not spam. And also they were classified as being non-spam. So those are the true negative. We have 688 emails that are spam and were classified as spam. And so on. So we have 212 spam. They are actually spam, but they were classified as not spam. And 127 that, sorry, I'm reading them the other way around. 127 that are not spam, they were classified as spam. And 212 that are spam and were classified as not spam. Okay, so out of those numbers, we can calculate the accuracy. So the accuracy is using the formula that I have put on the slide, slide 20. 23, I think it was. Okay, so these measures stand as you see them here. They're also calculated by R here. There are other measures that appear here, and I've added some interpretation on the slide for you. And then we have the kappa score that I've gone through with you that appears there. So 68, 57, and then we can look at the interpretation of what that means. So it's a substantial agreement. So it's considered a good model. And let's now look at testing this model. So using this model for prediction now. So we have the confusion matrix that looks at accuracy. And let's try to run the model on the test emails, on the test set. And we put that into P1. So we are running a prediction. And we are looking at another measure now, ROC and AUC. Why are we doing this? Okay, it's because remember what I was saying to you before, that you want to know that your model is not, the prediction are not due to chance. You want to kind of understand that, yeah? So the ROC curve, which stands for Receiver Operating Characteristics Curve, allows you to look at that relationship of your model. And the area under the curve is basically the area under this ROC curve that you see here. So this code that I put in there allows you to see the error of your model, the performance of your model in terms of how good it is to distinguish those true positive and the false positive. Yeah, so we are having specificity and sensitivity as the variables. And the other thing it allows you to do is to see the threshold point, which is the one that is indicated on the chart. Okay, so this is the point where the discriminative power of your model is high. Okay, so hopefully everybody managed to run this code, but if not, you can probably give some feedback. There's something in the chat. Let me have a look. Okay, so the codes should be in the same folder online. Really. If you've access. Yeah, so the code is in the folder. And as has been said in the chat, the SPAM7 dataset is part of the library DAG. So apologies, I think if I had, it will take a bit of time to get organized being the first session, and you didn't have this code before the session. So maybe if I can get a hands up who managed to run the code. If you can put your hand up, then I can check. Okay, 1, 2. Okay, so 2 people. I've managed to run 3. So maybe we can wait a little bit. I know we are still within the time of a session of 3 hours, but let's try to wait for people to manage to get the data set. Okay. So maybe let me get some feedback. Are people trying to run the code, or I hope people are not giving up. Maybe you can put in the chat. Are you trying to run the code now or not? I see some people have managed and they indicated they're running the code. Okay, good. And some people are managing. Okay, great. I don't have the script. It's in the Google folder. Let me just put it again there, but the script is there. Oops. Right. Yes, so apologies, there was a typo there. So instead of x equal class, put x equal yes, no. Florence, that's to Florence. And Ajulo, you download the code from the G Drive folder. Florence, I will correct that error there. Sorry for that. So instead of x equal class, you put x equal yes, no. Because what happened is I added another column before and I called it class, because yes, no is not numeric. So I had tried before to replace that and add a 0, 1 instead of yes, 1, no, 0. So that's what happened. But then I removed it, but I didn't clean up that plot. So while people are opening that, I have added on the slide some interpretation of the numbers that you see when you're running these models in terms of accuracy. So after you build the tree and you do print CP of that tree, you will see some numbers there. So you will see the classification formula that was used. You will see information about the variables. So here the variable actually used in the tree construction. And there was a good question there, you know, how do we know which ones? And hopefully if we have time, we'll go to those slides to show you a little bit how this algorithm works. But one thing that you need to note is that out of all those variables that were there, only 3 were used for the construction of the tree. The other thing you see there is the root node error. So that is the proportion of how many were positive or spam out of the total, 39. Okay, 1 minute. Okay, the other thing that you're going to see there is a table, and the table shows you some values. So CP is the complexity parameter, which is used, basically it describes how complex the tree is. And you want to strike a balance between the number of features and the levels. And that complexity parameter captures that. And then you have the number of splits to reach that point, right? So you can see initially there are 0 splits and the error is high. So you would expect with each level, with each split you do in the tree, the error goes down. And there are 2 types of errors that are being shown there. One is the relative error. So that's the error relative to the root node. So as I said, the error relative to the node goes down, to the root node, goes down with the splits. And the X error, that one is the cross-validation error. Okay, and there is a rule of thumb, okay, that I've added there in italics, yeah, that this measures the X error, the rel error, and the standard deviation, helps you choose where to prune the tree. So helps you, when I say prune, what it means, you cut branches out. So by that you mean you select which features to use, and you also select the height. And that is the lowest level where that relationship stands, that I've put it at the bottom of the slide. Okay. There's also some notes on how to interpret the confusion matrix. Now, if this is not clear enough, you can let me know. I will give you the email at the end of the session, and then you can tell me. You can send me an email. There's also a slide on how to read the ROC curve and the area under the curve. And I've put some notes in the code. But if you have questions, you can let me know also. Okay. How is everyone? I can see, but how is everyone in terms of running the code? Oh, there's a question. Oh, hand up.
Yes, please. It's just about these models. Do we have any assumptions and any model diagnostic checks?
Okay, what do you mean?
So when plotting such kinds of data, or from the beginning to the end, like when we started plotting the decision tree and now we are onto the predictive tree. So I was just wondering if we have any assumptions before plotting the trees and heading on to the prediction trees, like in other models, say the logistic models or linear regression models. Are there any assumptions we need to undertake when doing this kind of analysis?
Okay. Well, most measures that you see, most metrics that you see here do have an assumption that the data is normally distributed, right? So I'm not sure what you mean, what kind of assumption, but that's one assumption. So all these error metrics take that into account, because errors is things that are, outside of the expected, kind of range, right? So that's one assumption. The other assumption would be maybe in the data, right? So to speak, in how you chose those features, for example, because here you make an assumption that these features represent your email. Yeah. So your email, if you get a new email, you will be extracting the same features. So your model performs the way it does with respect to these features, right? So if that's why I was mentioning there that it's an iterative process. New features can be added, or as more emails are being looked at, one feature becomes more important than another, because you are, adding more messages to more emails to your data set, right? So what we are looking here, we are looking at the sample, right? We are looking at the sample of our data to build this tree. Hopefully that is answering the question. Couldn't see the code, right? So the code, let me just list these files a bit differently. Yeah, so the code is in this file called spamdt.r. That answers one of the message. So it's so I'm not sure, Anna, did I answer the question? Was I
Oh, yes, you did. Thank you so much.
okay? So before we go, as people are trying to pull the data, I'm wondering what we should do now. But let me show you how this tree was built. Yeah. Yes.
For the confusion matrix, on my screen, it show me that I have to set direction to control case, and I'm not clear on that.
Say it again.
When you run the confusion matrix R, for example, go down to the multi-case row.
Oh, here, yes.
Yeah, run that. It's what does mean? It says that setting direction control case. I didn't understand that.
Yeah, that's true. Yeah, so maybe just to say here, I mainly work with Python, but for this course, I was told I have to switch to R. So a lot of the codes I had were in Python. So I'm not entirely sure. If somebody's an R expert here, they could come in and tell us. But you're right. I think that's something we could look into. Let me look into it.
Okay.
Okay, yeah. So I think there will be recording. I was told that R is the tool of choice. So one of the examples you see in the slides actually is in Python later on in the slide. I just added in there anyway. But I switched them all to R. So let me go back to this algorithm. So this is the algorithm for building a classification and regression tree. Now on this slide, I was saying there are 3 different types of algorithm to build these trees. And they're all iterative. And I was saying before they can build more than one tree. It all depends on the sample data that you're looking at, and the evaluation metrics that are being used. So in the slides, I'm giving one example. So this CART algorithm, which is what R is using, works by recursively partitioning the training data into smaller subsets using binary tree. So these are always binary trees, this CART algorithm. And if you look at the tree that we had in R, it was a binary tree. So each node has at most 2 children. And this usually works for classification, right? That's what we have, 2 cases, yes, no. The algorithm, you can see that with each node that's being split, the training data set is split in smaller subsets that satisfy some criteria. So the tree starts from the node, so it builds the tree top down, so to speak. And initially, the root node has all the training data in it. So if you look at our algorithm here, right, we split into train and test. So how many? We have 2,296 testing observations and 2,305 training data points. So if you look at the node, we have 1,405 plus 900, which gives you 2,305. So in the root node, you always start with the whole training data set. And as you split the node, that data set gets split in smaller chunks. driven by the criteria in the nodes. So at each node, the algorithm selects a feature and a threshold that best separates the training data into groups. So how do we select this feature? We discuss in the next slide. Now, what you want to do is you want to select a feature that gives you the biggest amount of information about that email that you're trying to classify. So that's what you're doing. So you're iteratively building this tree. You split the node, and at each level, you select a feature that best splits your data set so that you can distinguish and classify those emails. When do you stop? So here, the stop criteria can be either a maximum depth that's being reached, or you don't gain much information. And if you remember that chart, that graph, where is it? I think it's coming soon at some point. I have a, let me see, maybe it's, I have not printed. Okay, let me plot. You see, this one shows you, you know, that at some point you plateau. So there's no point increasing the tree, you're not gaining, you know, information. So that's what's happening. Now, this CAT algorithm uses what's called a Gini impurity measure. And that's calculated for the whole data set, and then it's calculated for every single node and split that you make. Okay, so you keep doing that until you build the whole tree. So let's have a look at how it works. So first, what's the formula for this Gini impurity measure? All right. You have the formula on the left. So it's 1 minus, and then you have a sum of pi to the power 2. So C is the number of classes, right? And pi is the probability of a randomly chosen element in the node being labeled as one of those classes, class I, right? So you have 1 minus the sum of probabilities as being this Gini index. So let's have a look at this example. Now, this is not the spam email, it's slightly different. So we are trying to make a decision whether to buy a product or not based on the age of the customer and the income of that customer. So we have this little training data that you see here. And we have somebody of age 30 with an income of 20,000 who bought that product. Somebody who's age 40, an income of 50,000 who bought that product. And somebody who's age 20, income 30,000, did not buy it, and so on. So imagine that I want to build a decision tree for this scenario. Okay, so initially, let's say that I think there's some, I forgot to put something in here. So initially, you calculate the Gini index for the whole data set, right? But it's okay, we can still go with this example. So let's imagine that the first node, the first split that we want to do is based on age. Okay, so we say that we are going to start splitting by looking at the age. And coming to assumptions, because there was questions about the assumptions. You know, initially, how do you find out this threshold? Well, you can use some statistical measures to help you arrive at the threshold. But you can also maybe make a guess, for example. So in this case, you can say, all right, I'm splitting by age and I choose a threshold of 35. Yeah. So on one branch, you'll have people who buy the product, and on the other one, you have people who do not buy the product. So what do we have on the left of this node? So on the left of this node is all those who are less than 35. So let's have a look at the ones that are less than 35. So we have 20, 30. So we have two data points less than 35 to the left. Out of these, one of them buys the product and the other one doesn't. So the Gini index for the left is 1 minus 1 divided by 2, because the probability of somebody buying in that particular subset is 1 over 2 to the power 2 minus, and then again, the probability of somebody not buying the product is the same, 1 over 2. So we get the Gini value for the left, the Gini impurity for the left node. In the right node, we have 3 data points. So these are all the people over 35. So we are splitting now our data, right? Over 35, we have somebody who's 40, somebody who's 50, somebody who's 60. Now, out of them, 2 people buy the product. So that's 2 over 3 buy the product. And 1 person does not buy it. So that's 1 over 3. So we calculate the Gini impurity index for the right-hand side. And then we do a weighted kind of sum to get the index for the split, 0.48. So this would be, so there are 5 data points, 2 are on the left, 3 are on the right. So we do 2 over 5 G left plus 3 over 5 G right. And that gives us the impurity for the split. So this explains this calculation. So yeah, so for each input variable, we calculate the impurity for every split that we are doing. And which one are we choosing? Because you can have more than one split, right? You have different split points. So you choose the one with the minimum impurity value to split the tree. So basically that's what this algorithm does. For every input variable, you calculate the Gini impurity for all possible split points. And you always use the one with the minimum Gini impurity. So that's how you choose, you know, how your tree will look like, will be based on this. So as another example for a binary classification, let's suppose that we have a data set of patients and we have the age, the gender, the blood pressure, the cholesterol, and then we want to arrive at the classification whether they have a heart disease or not based on this information. So age, gender, blood pressure, and cholesterol level. So you want to build a decision tree to predict whether a new patient will have a heart disease based on these features. Okay, so to start, you calculate the impurity index for the entire data set. Yeah, so let's say there are 500 patients and 200 of them have heart disease and 300 don't. Okay, so the Gini impurity index is 0.48. Yeah, so we have 1 minus probability that one belongs to, has heart disease, yeah, 200, minus probability that they don't have heart disease, 300 over 500. So this is the root. Now, how do we split? So for every input variable, so in this case, we have age, gender, blood pressure, cholesterol level, we consider different splits, thresholds that we can have. Now, maybe here you're going to ask how are we choosing them, right? So there's obviously a theory about that, how you would choose and consider different splits. And it should be based on the medical profession, right? On the medical expertise with respect to these variables. And a lot of them may be based on statistical results that have been observed before. So let's do like in the previous example, we choose age as the first variable that we split on. So if we choose the age, we now have to think of thresholds. So we consider all possible split points and we calculate the Gini impurity, right? And let's suppose that we do that and the minimum Gini impurity is 50 years. Okay, so it means that we are splitting with 50 as the threshold. So two subsets, those that are younger, 50 and younger, and those who are older than 50. So we create two nodes for this subset. So you can see on the next slide. So we have age less than or equal than 50 and over. Now, what variable are we supposed to choose next, right? So we have to look to the left and we have to look to the right and calculate the Gini impurity for each node. So in this example, let's suppose that in the first node, there are 100 patients that have a heart disease and 200 don't. Okay, so the impurity for that node is calculated in that way. The next node, we say, okay, 100 have, 100 don't. So we calculate the Gini impurity for that side as well. And we choose the split that results with the minimum impurity index. Okay, and you keep doing this until you stop. So let's suppose that this is the tree that you come up with. So you split by age, then you can split the left by BP, the right by probably that's cholesterol levels, and you arrive at a decision tree. And this decision tree can help you predict whether a new patient will have a heart disease based on the three characteristics that are in the tree. Okay, so you can see that not all the features have been selected for this tree, for example. So that's a short kind of introduction to decision trees. So in R, it's fairly easy to build these trees, as we have seen. But we rely on the algorithm to drive that split. We are not manually creating it, of course. So maybe let me stop here to see if there are any questions and just to get some feedback from the room in terms of whether you've managed to run the code or where people are in terms of the code. Maybe I should say, is anyone here who hasn't managed to run the code or find the code? Okay, so maybe there's nobody. Okay, everybody has managed. As another example that I prepared for you, The reason I prepared these examples is because it's easier to understand the data as opposed to other large data sets that have complicated measurements. So we kind of get the intuition behind the data that we are using. So the next data set I prepared for you, the next example, but we are not going to run it here. I think I should leave this with you so you can run it over the weekend for when we meet on Monday. But this data set is predicting the weight from height and gender. So we have, let me go to R, apologies. Let me go to R now and open the other project. So let me close this project. And open the height project. Sorry. Yes. So it's good you're helping each other. So if you don't reckon, if the code doesn't recognize a package, just run install.package. Install.package is with the name of that package. So let me show you this other data that we have. Right, a fairly simple data set. And what we have in here is the gender of a person, the height in inches here, and the weight in pounds. But then we also have the height in centimeter and the weight in kg. So we are going to use the last two columns, which is the height in centimeters and the weight in kg. So we are using gender, height, and weight. And the purpose of this is to create a predictive model that predicts the weight of a person from the height and the gender of that person. You're going to ask me, why do that? Well, if you look a bit of, if you do a bit of research in the literature, you'll see that actually this is an interesting problem. It has applications. And a lot of these applications are to do with things like critical situations, maybe the intensive care units, where it's not possible to weigh a person before administering strict weight-based drugs or procedures. So I put some links to some papers. Yeah, I put some links to some papers that look into this issue. So what we want is to predict the weight given the gender and the height of the person. Now, the gender is relevant because it depends, right? But it tends that generally male are taller than females, right? So what I would like you to do is to use the second example, the second folder, and you have a file there that I will ask you to use for this example. So let me go in here, and you will need to install the RStudio. I saw somebody putting a comment on the group. You need the RTools, or the RTools and RStudios for this. It's good to install both of them. So I'm not going to go through the running of this, but you will recognize similar kind of instructions from the first examples. So we will have to extract a training and a test data set. We will decide which one is our variable for prediction and which are our independent variables that we'll be using for prediction. So we are extracting the variables of interest. So in this case, I was saying to you, we are using the last two columns. So the height will be in centimeters, the weight will be in kgs. And the first column is the gender. And the same for the test data. The first thing you're going to see there is that initially I'm running a linear model, a linear regression model, and I'm only using the height as a predictive variable. And further down in the code, I am building a regression tree with the same code that we've used before in the first example. The only difference would be that in the regression tree, I am adding the gender. So you can see here that, you can also specify which variables to use for your tree. Yeah, so in this example, I am predicting the weight based on the in kg, based on the height in centimeter, and the gender, and it's additive. So let me quickly run this just for the demonstration. So we see here that, the female tend to be less heavy than men and also less tall overall in this data set. Let's split. And you can look and see how the data set has been split. So there are 10,000 observations and they are pretty much equally split, test and train. And then you'll be picking the variables that you'll be looking at, and you'll be fitting the data. Now, in this example, I'm not distinguishing in this fit, line of fit, I'm not distinguishing between female and male. So of course, I don't know whether in this data points, I don't know whether I'm looking to the females or to the males. But one thing that you could do is you can look at the intercept and the coefficients of the line of fit. And you'll see here that I have 1.372 and minus 158.101. So my line, the equation of my line is this, which you see there. Now, this is not a classification. This is regression. So I'm not looking at the coefficients. I'm not looking, sorry, at the confusion matrix as I did before. I need a different measure for error. So the measure that is used commonly is the root mean squared error. And this is what you see that's been used in this example. Sorry, let me go back here. Right. So let me stop here because there's quite a lot for one day and leave you with these notes. And then hopefully people manage to run all of these, look at the notes that I've put in there. If there's need for more clarification, you can let me know. And we can pick these examples and discuss a little bit next time when we meet on Monday. So don't go through all the documents. They really should go up to 54, to the slide 54. Okay, thank you.
Excuse me.
Yes.
For this code, maybe if we wanted to make the trained data set 80% and the test 20%, how can we do that?
Oh yeah, to do a different split. Yeah, okay. Well, yes, you can do that by generating a split. If you remember the other example I had before, I was putting an equal chance for the data set to belong to either the training or the test. Let me just, I don't want to change the project, but where's here, you see? So I was looking at this probability. So it was an equal probability that it belongs to the training or to the test set.
Okay.
So you should be, yes. So you'll be able to change that.
Okay, thank you.
Okay. So let us stop here for today. Joel or Sylvia, there's been quite a lot of content.
Excuse
So
me.
let me leave you with the decision tree. So have a look at the building of the decision tree and the two examples. And then on Monday, we can resume by discussing this, and then we can also move on maybe to a different topic. Sorry, yes. Somebody was asking something.
Okay, I was just asking, are you also going to tackle things like the ensemble algorithms, things like the Bangi testing and gradient testing, such things?
Yes, I was planning. So first, I thought we should start with the decision trees. So this is only one tree, but there
Yes,
are situations where you would want to create an ensemble of
random
trees.
yes,
Yes,
and a random forest.
yes.
Oh, it's okay, thank you.
Yes. Well, I was thinking that since a lot of people I was told are beginners in machine learning, that we start with this first and then advance to the other topics in the next two sessions. It's quite difficult to capture something like this in 6 hours, because we have 6 hours for this section before you move on to unsupervised algorithms. So I thought it's better to go a bit slower on the first components that we need, which are these decision trees, and how we validate the models, how we look at accuracy and what those numbers mean, and then build up to the other topics in the next two sessions.
Would you go to the final code you gave us regarding the weight, height? Because for my screen, when I tried to run, I couldn't get the weight in kg. I don't know, maybe if I have error with my computer, I
Okay.
don't know.
Which line? Which line? What number is the line? Would you be able to tell me which number is the line that you were looking at? This one, 21, training weight. Hello? Okay, maybe it could be if you get an error.
Sorry, yeah, let's go back to line number 10 regarding the ggplot. Yeah, there I
Yes.
couldn't find the weight in kg.
All right. Did you add the data? Did you run the row to load the data?
I read it in different way, actually. I read it by just choosing the file where it is located, not actually this code. This code didn't work for me, so I read it in another way.
Okay, but do you have values in the data variable? Like if you click on the data variable, are they there?
Okay, let me check. Yeah.
So double click on the data variable, and are you able to see what I'm seeing?
Yeah, the weight is there, but when I run it, it said that it has error. I don't know.
What does the error say?
Let me tell you. Yeah, it said that object weight kg not found.
Do you have the dot at the end?
Yes.
Okay. I think it's maybe to do with the data then, the way
Yeah. Okay.
yeah.
I will check later. No problem. Okay.
Yes, I'm not sure what is happening. So yeah, let's stop here because now you have the files and you have the PDF, and maybe go through that and we resume on Monday. Joel and Sylvia, over to you. Oh yes,
Thank you.
maybe just before I go to you, in the PowerPoint, I think after the example slides, there's also my email. So if you want to email me with feedback, then please do that, or questions, you can email me. Thank you. Sorry, Joel, over to you.
Thank you very much.